So I will take you on a bit of a tour, as Mark says. So basically, the talk that my group are, it's a group of postdocs and students and undergrads. So they're based between Kiel University and here at Daisy, working on different projects. And as we go through the talk, then I will tell you about the different projects. And I'll also tell you about some of the users' work at P08. And then at the end, I'll tell you a little bit about our data initiative. So this is the introduction. So LISA is a liquid interface scattering apparatus, a double crystal monochromator with all the advantages and disadvantages that you get with such a device. So we can do really beautiful reflectivities on liquid or on liquid-liquid interfaces. We have very high beam precision, and we can look at very delicate interfaces because we don't have to move the sample during the measurements. And there's many different reasons that you would like to look at liquid interfaces. And I won't go through all of them now, but one is to try and understand ion repulsion. So if you think of the classical model of ion repulsion, it can't really explain ion repulsion in the atmosphere. And then if we look at more modern molecular dynamics simulations where highly polarized anions are discussed or how they are absorbed at interfaces, then you can see examples here. So we at Jungwirth and Tobias that you can imagine, or you would expect that there would be, instead of the classical theory of depletion, that there could be enrichment at the interfaces. And two of the classic examples here are sodium iodide and sodium chloride. And so these are systems that we are trying to understand as well. And I mean, we all know at surfaces and liquids, you have many things going on. You have polarization, we have our surface tension, and we're trying to consider all of these aspects. So for example, if we think of atoms or molecules or ions at an air-water interface, then the cations are repelled, and then they would be present in the sublayer. So this is well studied. It's not completely understood, but one of the aspects to try and really understand what's going on is to try and understand the dynamics at such a surface. And in order to go and follow this goal, what we did is we applied for funding and got funding to build up a pump probe setup at LISA. At P08 at PETRA III with Chen and Florian. So we have a femtosecond laser there. So for example, a typical experimental setup would be using the X-ray probe with 18 kiloelectron volts and then measuring in timing mode with 40 bunch mode using the femtosecond laser, which has either got its fundamental 1,300 nanometers or the second, third, and fourth harmonics. And we can set this up so that it's running synchronized with the synchrotron here at Petra, so that we have nanosecond sensitivity. So the laser itself is quite a beast. We chose something that was stable and not the most exciting laser in the world, but it has enough power that we have. There's a hand raised. Jaroslav, have you a question?
Yeah, I have a quick question. Bridget, can you control the polarization of the laser from linear to circular, for example, during your experiments?
No, unfortunately, that's not something we have a new nanosecond laser that we will install, and we might be able to do it with that, but we haven't tested it yet. But here it wasn't. We haven't tried to do it, but I'm almost certain that we can't. Yeah. So we usually use either the main harmonic or the first, second, or third harmonic. But if you're prepared, if you really need another wavelength and you're prepared, to take in the cost that you lose an awful lot of intensity. We can go from 210 to 2,600 nanometers, but you lose about a factor of between 10 and 100 in the intensity. So you really need to be tuned at a very determined wavelength that you need to excite something if you want to choose that. So that's like the basics of what we have. And so what kind of studies have we been doing with that? So we've been looking at laser-induced dynamics at liquid interfaces. So we've been looking at the ion surface distribution on solvation dynamics. And as you see from my earlier slide, we were taking the classical salt solutions, for example, sodium iodide, to determine the electron density profile and the surface roughness. And so what if we look at the roughness as we go through different laser different concentrations, we see that the roughness is increasing. And also if we look at the surface, of course. And if we go to the X-ray fluorescence, we also see that there is some effects, surface-dependent fluorescence behavior, and we have beam time running at the moment that we're trying to look at this time resolved. So, but in the first steps, we've been focusing on what happens if we change the power in the laser. So there's a classic equation here, of course, which all of you are familiar with, that we have our surface tension and that it's a function of temperature and also of electron density. And so when we tried to do this originally, we thought we would find some kind of surface layering, and if we excited the system with the laser, that we'd be able to follow some changes from enrichment at the surface. But if you look at our reflectivities here, you would see you would need a very, very extreme kind of imagination before you would like to convince anybody that there's actually a layer at any of these surfaces, regardless of the concentration or the laser power. But what we do see is that if we look at here, so you can see here the laser off, this is the black dots here, and when we turn on the laser, we have these colored dots here, so you can associate it going from black up to pink. We're increasing the laser energy pulse. And what we see is that when we do this repeatedly, we see that the roughness is going down. So this is not what you would expect classically, because we're increasing. With the laser, we would expect that we would increase the temperature, or even if we are causing some kind of depletion, then the roughness should increase. But actually, the roughness is increasing, and so this is saying that the surface tension is increasing. So we're at this stage now. We see this, but we can't say. We have some timing now. That's what we were looking at actually this week. So this paper is submitted, but this is the static work. And we see timescales, we see effects. They're not. They're really. It's dynamics. It's kinetics rather than dynamics. It's collective behavior. We see effects, strong effects over timescales of sub-second or seconds. But when we go to the faster timescales, either we do not see effects that we would expect, or we still don't have the sensitivity. So anybody who is working with liquids can tell you, as you all are, that it could be either case. So hopefully I can give you more on that in the near future. And also we've been looking at.
Can I have a quick question, please?
Yes, sure. Go ahead.
So how can we understand that in simple terms? You know, is it due to the alignment of the molecules in the solution or constituting the solution by the electric field of the laser beam, or is there some kind of other hypothesis regarding that?
So yeah, so we're trying to at the start we started with we tried to get really to excite the molecules themselves with the, that's why we take the 258 nanometers. So we're really trying to create an electronic excitation at the surface, but because we don't see what we expected was that we would induce some charging at the surface, and we would pull the molecules to the surface, and we would see a layer forming, but the effect is not that strong. So we don't see a layer, but we definitely see that there is an enrichment at the surface. So so to try and understand that further, we want to look into the time scale and see what's happening, because either something's happening much faster, and then this is the relaxed state after the event, or the polarization at the surface is instantaneous, and then it stays like this. So I don't have all the answers yet. Yeah. I think if you catch me on some days of the week, I can argue both sides of the case. It's a bit like being on the school debating team, and so we're really searching for the evidence and also the simulation, so we can be definitive about which way we want to go. This is why we held off with the kinetics paper. And on the other hand, now, if we go to liquid metals and take mercury, here we can really see effects on the sub-nanosecond time scale. So they're small, but at the layering, we can see. So now we've moved away from the salts. We're going back to the classic little liquid metal where we have layering, and so we thought here we would have two chances, because here in the lower region we're sensitive, typically very sensitive to the roughness, to the capillary waves effects, and if we go above 2, then we're very sensitive to the layering in itself. And as it happens, we can't see so much with the capillary wave on this time scale, which is consistent with what we saw in the salt solution, that we didn't see effects on the nanosecond time scale. But we do see here at the layering, we see that we get an increase in the layering. So if we go, so we see an increase in roughness in the layer. So this is going then here, this is minus 3 seconds. So this is before the laser arrives. And if we go then down to the black, down to 3 nanoseconds afterwards, we see. So these are really reflectivities that were collected step by step with pump probe. So this is really quite incredible. Until you've measured it, you can't believe how difficult it is. So what we see here is that on the short time scale, there is something happening to the layering, yeah. And again, it's really hard to describe exactly what's going on, but if we use the distorted crystal model and look at the intrinsic roughness over this time delay, we see that there's, yeah, so we can argue about the intrinsic roughness, whether it's constant or whether there's a slight increase. But if we look at the layering decay parameter, we see that the layering decay parameter, that the roughness is increasing and then recovering again as we go to longer time scales. So this is what we're trying to describe at the moment, and also so we can go and sit at one position in the reflectivity and then look at the dynamics at that position. So so this is an R over RF. So it's nice to make the quasi-Bragg peak look more impressive. And now if we either go at 1.5 or at 2 inverse angstroms, so this is here, this is the famous, let's say, where we would end up getting the beach from this bump here. And this is then here focused more again on the layering. And again, at both of these Q values, we see that there's a decrease in the intensity and that it recovers, but not quite to the original value again on the second of time scale. So this is the second evidence that we really see an effect. And here at the front, where we would also like to measure, that's quite difficult because it's much harder to keep everything well aligned there. So we're not so sure if we trust that data. Well, it's not that we don't trust it, but the error bars are larger when we do the fitting. So this is where we see the best effects. So otherwise, I know you would like to see how does it look here, but if I show you the data from between 0.5 and 1, then you won't see much. You might imagine there's something going on. So we focus on this for now, and so that's what we're trying to describe now, how this process is driven. We don't have all the explanations, but I definitely it seems that this is so there's a less of an effect at the front. So it's not a heat-driven process. It's really an electronic excitation of the layering peak. Otherwise, we would see the same behavior at the lower Q values. So that's just to help you and understand what we can do on the time resolved method. And of course, there's a lot of work to be done here. We've developed a flow cell because we've discovered with the salt solutions that beam damage and laser damage is a big effect. So that's what we have running at the beam time at the moment now. So we can refresh the salts very easily. The fluorescence detector is integrated into the sample cell with the shutter, so we can swap between the fluorescence and the pump probe measurements and do combinations with fluorescence measurements. And yeah, we will have some solar slits. Actually, we expected them to be delivered in December 2024, but they haven't arrived yet. So now we have March. So I hope they'll be here before the end of this month. And we also have a project where we're working on a new fast shutter and a waveguide. And we have a new nanosecond laser as well. So that's the first bit of the talk where I wanted to talk about the exciting developments on pump probe. And you know, working with liquids is not always easy. So one of the projects we have is to try and help the users and the non-expert users to come and do experiments by using automation in reflectivity at liquid surfaces. And this is a collaboration with Chen here at DAISY, and also together with Karen Elder at Lund and Tom Arnold from ESS. It's a joint German-Swedish partnership where we got funding to work on what we call our Uperals project, achieving reproducibility and precision measurements. And we want to be able to do a direct comparison between the X-ray and the neutron experiments. And in this project, what we are focusing on is on the X-ray side, on switching of glycolipid membranes. I'll give you some examples in a minute. And on the neutron side, Karen is focused on amphiphilic behavior in deep eutectic solvents. So the idea is to build similar systems at the X-ray and at the neutron source, and then to exchange the experience in the automation. And so we're waiting for our new Langmuir trough at the moment. And in preparation, we're also working on flow. So this is not just for the simple system with the Langmuir trough, then you would use an aspirator and apply from the top. But we also want to be able to exchange the sub phases. And this is also very applied to our pump probe measurements. So we have developed a sample cell, and we're very worried about that when we do the laser experiments in particular, we're worried about losing the quality of the sample before we notice that it's gone. And so what we have here is a sample with temperature sensor, pH sensor, and a Wilhelmy plate to measure the surface tension as well. So you can put them in and out, and a humidity sensor as well. So this is really very nice, and this technology will be transferred then from the flow cell into the Langmuir trough when it arrives. And I mentioned then the photo-switchable lipids, and these are our model system for the X-ray reflectivity system. And what we've been doing now for the last few years is we've been putting azobenzene components into glycolipids, and then we can put them into lipid membranes, for example, DPPC, and then by using visible or UV light, then we can switch them. And so this is here pictures of the surface tension, and you can see if we sit at 18 millinewton meter, and then we can switch between the trans and the cis state backwards and forwards. And if we go down to a lower pressure of about 12, we see an even stronger switching effect. And then something very interesting happens if we go even lower. So we're going below this phase transition here now, and we still see switching. And if we look closely at the switching, you see that it's reversed. So we have a bipolar switching in this system, and the reversal occurs then regardless. So here we see that the cis increases the surface tension, and now we have the reverse effect when we go below this phase transition, which we call phi. And this occurs for both trans and cis. So basically we can divide our sample into three zones, into three phases with regard to how the switching behaves. And we see different switching behavior in these three zones. And if we look at the X-ray, the corresponding X-ray reflectivity and scattering length densities, we see that if we go to for higher molecular area, and then if we go down, so at 70, you see there's not much change, but as we go down, we see that the length of the molecules is actually increasing when we change from trans to cis. So we're trying to understand what is the process, because this could be very interesting for controlling membranes, for example, for applications such as drug delivery. And so if we have our azobenzene molecule, this is the model that we propose in a less densely packed system than the azobenzene containing phosphor glycolipid will tend to want to lie a little. And then when we switch it, then it moves up, so that the area that's available for the other molecules in the membrane is increased. And so therefore we see a decrease in the surface pressure. And on the other hand, as we go to higher compressions, when we switch the molecule, then we see the opposite effect. And when we switch the molecule, we get an even more compressive state. So this also explains why the effect at the lower pressures is much less strong than the effect at the higher pressures. But there's still many questions open here. For example, what is the orientation of the glycoside, and where exactly is the position of the switch in the monolayer? Is it really, as I've drawn here, are the heads really here? Is the azobenzene down here, or is it switching in the tail? So this is the main focus of Jonas Warrius' PhD thesis. So Jonas also built up the pump probe laser in his thesis, and this is also his work. And it's being carried on now by Svenja Huvelman, who has carried on with this system and extended the zone of our examinations to try and follow up on these open questions, really going into understand exactly what's going on at the phase transition for the trans and the phase transition at the cis, reproducing the same results that Jonas could do, but then going into the detail, using the two box model. She can see that there's an asymmetric thickness change between the head and the tail group, but if we look at the data really closely, we see a decrease in the head thickness, and this suggests an reorientation of the glyco head group. So this still doesn't really explain everything, and so we've been using some grazing incidence diffraction as well to try and see if it's really true that the molecules are actually moving apart from each other when we're going through the switching process. And indeed, using the grazing incidence diffraction, we can confirm, we can now, between a combination of X-ray and neutron reflectivity, we can see that the switching is between the head and the tail, and we can also confirm that this increase in the difference between the head groups is for real. So that's telling you about what I do. And now, before I swap over to talk about the FAIR data, I would like to tell you, give you some updates from what the others have been doing at our beamline, and Mimre and Sabuja Chowdhury have been looking at a solution processed hybrid lead perovskite films, which are very interesting for solar cells. And here you can really see that to form these lead perovskites at the liquid interface, it's very important to have steric acid. Otherwise, without the steric acid, we don't see a layer forming. And with the presence of steric acid, we can really see beautiful, not just reflectivity, but also grazing incidence diffraction. And similar, but not the same, Sajal and Ajit Sit from Shivnadar have been looking at the assembly of graphene oxide and a reduced graphene oxide in phosphor monolayers at the air-water interface. And here it's very interesting that there's a completely different assembly, regardless of whether we take graphene oxide or reduced graphene oxide. So if you see here, if we have the reduced graphene oxide, it tends to go between the DPPC, and the classic graphene oxide likes to form sheets underneath it. And this is something we can justify through the X-ray reflectivity measurements. And of course, it's got very interesting applications for antibacterial activity or for biosensing. And I think Moshe, Ben is here now, I see. We've been also doing some work with Moshe and Ben over the last few years. And this is a recent paper that was published together with Moshe on the ordering of ionic liquids at charged sapphire interfaces and the evolution of the cationic chain. And this young scientist here may be familiar, it's Diego Ponti. And here we were looking at room temperature ionic liquids, going over all different chain lengths to try and understand the structure. And what you can see here is that we see that the layer spacing contraction increases at both the surface and the bulk as we increase the chain length. And then the negative charge sapphire surface compresses the layers, and this increases the layering structure and also affects the intralayer structure. And this is probably here we were trying to figure out whether we had a perfect sub-bilayer or if there's intermingling between the layers. And looking at the distances between the thickness of the layer, then this is for sure that it's not a perfectly separated bilayer. So that was, I wouldn't say it was all the science, but this is some little highlights. And now in the remaining part, I just want to take you a tour on what we can do with FAIR data. And I want to tell you about Daphne for NFTI. This is data for photon and neutron experiments. So we're not a single consortium trying to work with data. This is actually funded over all different aspects of philosophical science, health, physical science, and engineering. So Daphne is here in the engineering side with our colleagues from FAIRMAT, who you may know are running this Nomad catalog. And what do we want to do with Daphne? So our aim is very honorable. Our aim is to make all photon and neutron data fair. And the reason that we want to do this is to enable better science. And to do that, we carry out a certain amount of measures. And this is to try and specify and collect high quality metadata at the point of the experiment, to provide curated metadata and data repositories, but not only the data, but also to provide the possibility to share software by providing curated repositories for managed software to share it between the community. And in order to achieve this, we need, of course, to do lots of education and training in research data management and connect out within this group of consortia that I showed you, then within our national and also into international organizations. And this Daphne project came together from, we have a committee for synchrotron research and a committee for neutron research here in Germany. And these are two user-driven organizations which work together between the facilities and the funding organizations and the government. And together with then the facilities, the synchrotron and free electron laser facilities in Germany, and also the neutron facilities in Germany, we set up a consortia together. You can see here logos from around its 16 different partners. Many are from large-scale facilities, but many are also university groups around the country who are working on very strong method development at the facilities. So it's a national, it's distributed funding for a common focus. And what brings us together and what is our common focus? And this is because we have a common research data workflow. So if you do an X-ray or a neutron experiment, first of all, you write, of course, a proposal, and then you have to go to a large-scale facility. So these large-scale facilities where we all go to do our experiments or where we work, they can provide a nucleus for educating people and teaching them best practice. So we focus on different points of this process, on the data collection, storing the data, evaluating the data, so that in the end, there's a good high quality publication at the end, and we make the data available in a data catalog. So if we think about how we can manage data production, so when we want to capture the metadata at the experiment, and this we need to have access to the control software, and also the aim is to have common data formats so that we can, if we think of the FAIR principle, FAIR means that the data is findable, A, that it's accessible, I is interoperable, that you can use it on different systems, and R is reusable. And to make it interoperable, having common data formats is very important so that you can get the data from somewhere else and you can still fit it into your analysis program. Collecting parameters sounds easy, but if you really think about it, do we get every single parameter from our sample? How was it produced? How was it made? getting the data from the instrument. If you really want to have everything recorded, you have to rethink it a little bit. And also you want to record what's going on in your environment. And for the users, it's very important to document the workflow. And this can be done using an electronic logbook. And so we've been working in the last 3 years, we've been working on developing what kind of needs are required for electronic logbooks. How can we prepare persistent IDs for samples? This is working together between Kiel and the IGSN link into DataCite. Data formats, looking at Nexus and OpenPMD standard, and really capturing metadata, standardization of metadata and automatic capture at the facilities. And we're now at the stage that these things on the left have been adopted for individual use cases, and now we have to spread it out to the whole of the community. And on the other aspect then is once we have this metadata, we need to be able to store it in repositories and catalogs. Again, this is moving along now. If we have the data and it's findable and accessible, then it has to be in a catalog so you can get to it. And you want to have high quality data, so you need to be able to curate it. You need to be able to validate the quality, and then you need to be able to store and archive the metadata and the data, and to provide access. And this is also important to think of what kind of access models you have. Is it open or is it controlled? For example, as standard in Europe, we have a 3-year embargo period, and after that, the data is expected to be free. And so to this end, we've been working on metadata catalogs, which are now available at all the facilities here, adopting agreed common search APIs. We came up with a recommendation for CICAD as a metadata catalog. It's running here at DAISY and at MLZ. And our colleagues in Berlin had already started using ICAD, which has been running at ESRF for some years now. We felt that the more modern CICAD would be a progressive approach, and this is why we recommend that people use CICAD. We're also working on public metadata catalogs. We have, at the moment, we have 3. We have one for reflectivity, one for XAFS, and one for XPCS. And these catalogs will be embedded in the European Open Science Cloud. We just got nominated to be one of the candidate nodes for both national nodes through the NFTI and also for PAN data in the PANOSC node. And this is something that we would do with this public data catalog, which is based at DAISY. So now it's set up, and the next job is to populate it. So you're all invited to put your data and your metadata there and then refer to it so that we can set up a community reference. And so up to now, as I say, we have like hundreds of data sets, but our aim is through the embargo period then is to create about 3,000 data sets that would be created of high quality. This is related to the number of publications that we have across our community per year. And not only the data, but also the software should be reusable. So when you analyze your data and process it and visualize it online, you need some tools. There's one very excellent tool which has been provided by the Free Electron Laser, the European Free Electron Laser. It's called DAMNIT. This is really excellent, providing an overview of your scans. You can forget about your Excel sheet. This is similar to the system that's built in at LCLS. It allows you to do pivot tables between your different parameters and plots, and it's very useful for giving visualization and organization. There's the PyDDAS software analysis. We're developing a lot of artificial intelligence analysis pipelines using ReflectTorch. And also this is with Frank Schreiber from Thüringer, and containerized development. For example, the CRISFEL software from Tom White here at DAISY is platform independent. So we try to make it easy for everybody. And to make all this happen, we have to do a lot of outreach. For example, we had 33 events in the last year. You can find us on LinkedIn. We don't have X. We are trying to get into the universities. For example, we have data management topics in the curriculum. I hold a master's course on data management at Kiel. We have similar things at KIT and in Siegen. We provide lecture material for our colleagues who wish to do the same. And we have strong links to research collaborations, large ones here in Germany and to graduate schools. And our annual meeting will take place shortly, but I think it's a bit far for you to travel just to find out. But we can tell you the next time we meet. And what might be interesting for your students and postdocs is that in October this year, we will provide a seminar in Bad Honnef on data and artificial intelligence and analysis in photon and neutron community. So we have strong links to some of the other consortium in NFDI, for example, FAIR and the engineers and chemistry, and to the particle physicists and astrophysics because they're here at DAISY. We also reach out to a community called IROM Data Community. This is all the large-scale facilities in Germany through Helmholtz to the DPG, that's the German Physical Science Organization, and internationally focused on Europe, the European Open Science Cloud, the European Synchrotron Users Organization, the European Neutron Organization, and the equivalent LEAPS and LENS for the facilities. And we worked very hard to provide an international community-wide paper from the European Synchrotron and Neutron community together with Andy Gotz from ESRF. And this is now published in IUCRJ, and it came out at the start of the year, and we've already had over 1,500 downloads. So it seems that people are really interested in finding out how you can make your data fair. And here we discuss what are the responsibilities of the users and the responsibilities of the large-scale facilities, and how we can move together into the future to provide sustainable solutions. So now you're asking, okay, but what does all of this have to do with X-ray reflectivity and liquid surfaces? And so that's what I would like to leave you with, is how we can apply this, the best practices for fair data collection and storage using X-ray reflectivity as an example. And this is combined work of Kiel and Turing, Frank's group, based here at P08 at DAISY and also at ID10 at the ESRF. So life starts, you've written your proposal, and then you come to the synchrotron with your sample. And hopefully then when you have your sample, first of all, you will record it with an ISGN number. And this provides the information on your sample for your later publication. You use an electronic laboratory notebook, and this is what we have described in the Synchrotron Radiation News in 2024, where also you have your beamline paper. The raw data is saved in a common format, so we recommend that it should be saved as a Nexus format. And now when you extract the data, sorry, this graphic seems to be a bit messed up, but when you extract the data, you want to have not just the metadata from the raw data, but you also want to be able to describe how you fitted the data. So you have to keep putting more metadata into the catalog and defining this metadata that's collected at the point of the experiment, something that needs a lot of community and facility and user discussion. And we have a white paper published by Wipke Lostrom and other members that you can find it on the Daphne at Zenodo homepage. Now, when we do the fitting and the modeling, we want to have a repository for the software. When we also publish, then we want to be able to publish the data so that when you publish you don't just have a publication, you also have the data, which can be found at an open data bank, and the software, which you can find in a software repository, and the information on the sample and how it was produced, which is stored in the ISGN, or the persistent ID describing the sample. So you can see this whole process will bring us to making the data more available and reusable. Additionally, by using automatic extraction and machine learning prediction programs, we could successfully implement a closed loop system at ID 10. So it's almost at that stage at P08. It still needs a click because of security issues, since the cyber attack at HZB, the Helmholtz Institute in Berlin last year. We have to be very careful what we can do and how the different systems at the synchrotron can speak to each other. So this is the whole process of how we visualize that for each paper. And there's one example here of a FAIR data publication from Svenja's small angle scattering work, and that's in IUCRJ from 2024. So now you see how we can get there and make the data fair. And so the aim, we really want to try and understand how we can understand liquid structures and their dynamics. We can see that there's a rich response to the laser excitation on water at sodium iodide and sodium chloride surfaces. We're also investigating many other salts, but don't want to tell you everything, or the time would be definitely over. We see different timescales for dynamics in different systems, depending on whether it's really dynamic or kinetic behavior. We have updated our X-ray chopper system now so that we can continuously measure over all timescales. We used to have a gap, and now we have no more gaps. We can go all the way from nanoseconds to seconds. And I was also telling you about our phospholipid systems, and there we also see that we have reversible structural changes by light illumination, and we have different timescales depending on how we do the switching. When we think about what we are doing, not just on the science, but also on the experimental side, we want to build up automation to make liquid science more accessible, and to work to make the data fair so that we can make the data that we do have more useful. So with that, thank you very much for your attention.
Yeah, thank you, Bridget, for that exciting talk.